Here's the first example of a problem in complex arithmetic. Okay. It's time harmonic waves. The complex arithmetic becomes necessary when you look at it an outgoing impedance boundary condition or a rebound boundary condition or a first order absorbing boundary condition like this. There's an I omega here. I is the imaginary unit. Right? Okay, so we're going to solve the Helmholtz problem in this tutorial on this domain. Okay. You see some sort of object. This is supposed to be a metallic object that will reflect waves, and we'll put a pulse somewhere there, and we'll see how that works out. The finite element space, again, is a Lagrange finite element space. And you have a pulse that's placed right there. Now you have to really zoom in to see it. Okay, you see the pulse. Okay, and let's open up the visual menu just in case. In the visual menu, you can increase the subdivisions. That asks the graphics window to plot more points, especially useful. It's especially useful when you have finite elements of high degrees. Okay. Okay. Here is a you integrate by multiply by test function, integrate by parts, as we do usually in finite elements, and you come up with a variational formulation for the Helmholtz problem. Here's the low order term. Here's the term coming from the boundary condition with the complex I omega, and the bars indicate complex conjugations and so forth. Everything we saw previously applies. You can do grad u, grad v, dx, except that note that we're not doing the complex conjugation because this is supposed to be a proxy function where basis functions are put in, and even if you're working in a complex space, the basis functions are real. Then you have omega squared uv here, and then you have the I omega uv on the boundary. And if you look back at this example, this geometry has a boundary here, a boundary here. We only want to put these boundary. This term corresponds to only integral over the outer boundary, and to say that we use ds with the argument outer, right? Okay. The source term consists of this pulse that I zoomed in previously, the little pulse over there. And then we solve, and then we get a solution that looks like this. Okay, let's explore the solution a bit. I go back to a higher subdivision, and then, sorry. Oh, okay. Sometimes, in order for the new grid function to appear, you have to close the visual menu and bring it back up. Now you see that the computed U has appeared as an option to plot here, and U has been split into U1 and U2. These are the real and imaginary parts. Okay, so you can visualize only the imaginary part if you like, or visualize only the real part if you like. Okay. Minus, the limits of the solution are minus 3 10 to the minus 2 plus 2 10 to the minus 2. So you could try and see if you can put your own limits here. And then turn off auto scale. Okay, I guess. Let's see. Play around with these scaling so you can see the waves a little better. And the other thing you can do is turn on deformation. Okay, this is, if you turn on deformation, let's see. You can, okay, well, maybe a little bit more. Okay, you sort of see the waves in whichever way you want to see, either as a patch plot or as a surface plot. Let me go back to without the deformation, and I want to show you one more feature here. For time harmonic solutions, this feature is very useful. This multiplies the solution by a time varying signal of e to the minus I omega t, or omega is something fictitious, that not the same omega that you see here, and you see the waves coming in, I guess, hitting and getting reflected from this metallic object and so forth.